Hi, hello. My name is Mohammad Nadeem from Mechanical Engineering. My tech talk topic on CFD simulation of fuel cell thermal management systems, and my subject of this tech talk is computational fluid dynamics and mechanical engineering applications. CFD simulation of fuel cell thermal management systems, an overview exploring the vital role of computational fluid dynamics in optimizing fuel cell performance and longevity. Understanding fuel cells principles and applications. Fuel cells are electrochemical devices that convert chemical energy directly into electrical energy, heat, and water through a chemical reaction with a fuel source, typically hydrogen, and an oxidant, usually oxygen from the air. Unlike batteries, they do not run down or need recharging. They produce electricity as long as fuel is supplied. This makes them highly attractive for various applications. Hydrogen and oxygen combine to produce electricity, continuous power generation with a constant fuel supply, high efficiency, and low environmental impact. The figure shows how if electricity produced from fuel cells in automotive, in stationary power, in portable devices. In automotive, clean and efficient power for electric vehicles, stationary power, reliable and decentralized energy solutions for homes and industries, portable devices, extended battery for life for laptops and phones. The critical role of thermal management in fuel cells. Maintaining optimal operating temperatures is paramount for fuel cell efficiency, durability, and safety. Inefficient thermal management can lead to severe performance degradation and premature failure. Efficiency loss. Overheating can significantly reduce power output and increase parasitic losses. Component degradation: big temperatures accelerate the degradation of membranes, catalysts, and other vital components. Safety concerns: uncontrolled heat can lead to critical failures. Failures. Pollution hazards. Water management. Water management temperature control to critical for balancing water content with a cell and drying out, preventing floating or drying out. Introduction to computational fluid dynamics for thermal systems. CFD is a powerful numerical method used to analyze and solve problems involving fluid flow, heat transfer, and associated phenomena in the context of fuel cells. It enables engineers to estimate and predict temperature distribution, fluid velocities, and pressure drops within complex thermal management systems without the need for extensive physical prototyping. Predicts fluid flow and heat transfer patterns, reduce development costs and time, provides detailed insights into internal dynamics by creating virtual models of fuel cell components. CFD helps identify thermal hotspots and optimize cooling strategies, ultimately enhancing overall system reliability and performance of this. Modeling approaches for fuel cell thermal management. Various CFD modeling techniques are employed to accurately represent the intricate thermal behavior of fuel cell systems, each offering different levels of detail and computational expense. Porous media models simplify complex structures like gas diffusion layers and catalyst layers into effective porous regions, reducing computational costs. Conjugate heat transfer simultaneously solves fluid flow and heat transfer in both solid and fluid domains, crucial for accurate temperature prediction. Single-phase and multi-phase flow models. Single-phase pollutants, example air, water, or multi-phase flows, boiling pollutants for advanced cooling strategies, stack level simulations, external analysis for single-cell center fuel cell stacks, considering interthermal interactions and manifold designs. Key parameters and performance. Effective CFD simulation for fuel cell thermal management really, really and accurately defining crucial parameters and evaluating key performance indicators to ensure design optimization. Temperature distribution identifies hotspots and overall thermal uniformly across the cell and stack. Pressure drop quantifies the energy required to pump coolants through the system, impacting process. Heat transfer coefficient measures the effectiveness of the heat removed from the fuel cell components to the coolant. Coolant flow rate and velocity and thermal stress. Case study 1. Optimizing cooling channel design. In the case study, CFD simulation were used to explore various cooling channel geometries within a fuel cell bipolar plate. The objective was to minimize temperature gradients and reduce pumping over while maintaining effective heat removal. Conventional circumference channels, high pressure drop, moderate temperature uniformity, parallel channels, low pressure drop, but poor temperature uniformity due to unequal flow distribution. Bio-inspired fractal channels achieved significant improvements in both temperature uniformly and reduced pumping power by mimicking natural branching patterns. The simulation results demonstrated that innovative designs behind traditional approaches could dramatically enhance thermal performance. Case study 2. Impact of material properties on thermal performance as gas diffusion air GDL bipolar plates thermal interference materials. Gas diffusion air GDL higher thermal conductivity GDLs lead to improved heat spreading and reduced local hotspots but also impacted reactant distribution in bipolar plates using materials with enhanced thermal conductivity. Example graphite composites metallic alloys significantly improved heat transfers efficiency away from the active cell area. Thermal interface materials optimization of interface materials between components played a crucial role in reducing contact resistance and facilitating heat flow. Challenges and future directions in fuel cell CFD simulations. While CFD offers immense value, several challenges persist, including the complex multi-physics nature of fuel cells, electrochemistry, fluid dynamics, heat transfer, and structural mechanics, and the need for more accurate material models. Computational cost for large-scale stack simulations remains a significant hurdle. Multi-physics coupling, integrating electrochemical reactions with the thermal and fluid dynamics validation data, availability of experiment data for robust model validation, computational expose, reducing simulation time for complex transient scenarios, advanced materials modeling, novel materials with antistrophic properties, future directions involving leveraging machine learning for faster simulations, developing modes sophisticated multi-scale models and enhancing simulation fidelity to real-world operating conditions. Personal answer concluding remarks towards sufficient. The future of energy lies our ability to innovate, integrate sustainable technology, and CFD is a key enabler in this revolution. Thank you.